Bagnal daw, civil engineers of the future. Welcome to your online class in hydraulics. I am your instructor Daryl J. Amble-Bean. In this video, I will solve sample problems in total hydrostatic force on curved surfaces. The tank shown is 3 meters wide into the paper. Neglect atmospheric pressure. Unit weight of water is 9.79 kilonewtons per cubic meters. Determine the nearest value to the A. Vertical component of the total hydrostatic force on the quarter circle panel AB in kilonewtons. B. Resultant hydrostatic force acting on the quarter circle panel AB in kilonewtons. And C. Angle that the resultant hydrostatic force makes with the horizontal in degrees. We have the water surface, and 4 meters below the water surface is the quarter circle panel AB with a radius of 5 meters and center at point O. In letter A, we are asked to solve for the vertical component of the total hydrostatic force, and that is Fv. And it is equal to gamma V, where gamma is the unit weight of the liquid and V is the volume, whose area can be found by tracing a vertical line from the endpoints of the curve up until the liquid surface. So from point A, we draw a vertical line up until the liquid surface. Same with point B. From point B, we draw a vertical line up until the liquid surface. And this is the area we will consider for the volume. We multiply this area with the width perpendicular to the paper. And in this problem, it is given as 3 meters. So for the volume, the area being considered is the area of this quarter circle plus the area of this rectangle multiplied with the width perpendicular to the paper, which is 3 meters. So let's substitute. For the area of a quarter circle, that's equal to pi r squared over 4, where our r is 5 meters. And for the area of the rectangle, that is equal to base times height, where our base is 5 meters and our height is 4 meters, multiplied by 3 meters. Therefore, volume is equal to 118.905 cubic meters. Now we're ready to solve for our FV. The unit weight is given in the problem, so we use 9.79 kilonewtons per cubic meters as our unit weight. Multiply that to the volume we computed. So therefore, Fv, or the vertical component of the total hydrostatic force, is equal to 1,164.08 kilonewtons. If we try to draw that in the figure, this is Fv. In letter B, we are asked to solve for the resultant hydrostatic force, which is equal to F equal to the square root of Fh squared plus Fv squared. But we don't have Fh yet. So we first solve for Fh, which is the horizontal component, which is calculated by the formula Fh is equal to gamma h bar area, just like the total hydrostatic force on plane surfaces. So we need our h bar. So first we need to project our curved surface. If we project that, it will be a rectangle with a base 3 meters. The base 3 meters is from the given width perpendicular to the paper, which is 3 meters. So we need to locate the center of gravity, CG. The height of the rectangle is 5 meters from the radius of the quarter circle. So if the height is 5 meters, the CG is 5 divided by 2. So we have 2.5 meters. CG is located 2.5 meters from the top of the curve and 2.5 meters from the bottom of the curve. So recall that h bar is the vertical distance from the liquid surface to the CG. So to get h bar, we simply add 2.5 meters and 4 meters. So that is equal to 6.5 meters. Now we're ready to solve for FH. But before that, let's try to illustrate FH on the figure by first locating CP, which is below CG. And along CP is where FH acts. And the resultant of these two components is F, or the resultant hydrostatic force. And the angle it makes with the horizontal is theta x. Now let's go back solving for our FH. So substituting, our gamma is 9.79 kilonewtons per cubic meters. Our h bar is 6.5 meters. And the area of the projected cross-section is the area of this rectangle, which is base times height. Our base is 3 meters, our height is 5 meters. Therefore, FH is equal to 954.525 kilonewtons. Now we're ready to solve for the resultant hydrostatic force by simply substituting our FH and our FV. Therefore, our resultant hydrostatic force is equal to 1,505.39 kilonewtons. And finally, for letter C, we are asked to solve for theta x, or the angle that the resultant hydrostatic force makes with the horizontal. So we simply use the formula tan theta x is equal to FV over FH. So simply substituting our FH and our FV, we get theta x equal to 50.65 degrees. The 5-meter wide sluice gate AB shown, tangent to the vertical wall at A, holds back water. The surface of the gate in contact with the water can be taken as part of a cylinder with radius 4 meters. A. Determine the horizontal force acting on the curve. B. Determine the total force on the curve. And C. Determine the location of the vertical force from point A. We have the water surface. 1 meter below the water surface is the sluice gate AB, which is tangent at point A, with a radius of 4 meters and a center at point C with a central angle of 30 degrees. In letter A, we are asked to solve for the horizontal component of the total hydrostatic force, or simply the horizontal force FH, which is equal to gamma h bar area. But first we need to solve for h bar by projecting the area of the curve on the vertical. which is a rectangle with a width of 5 meters, based from the given 5 meter wide. And we determine its height by solving for this vertical distance. We can solve for this vertical distance by considering this right triangle. And this distance is equal to 4 sine 30. And that is equal to exactly 2 meters. Therefore, the height of the rectangle is 2 meters. We now locate the center of gravity CG of the rectangle. If its height is 2 meters, the CG is located 1 meter from the top of the rectangle and 1 meter from the bottom of the rectangle. We also have the center of pressure CP below CG, where FH acts. For H bar, that is the vertical distance from the liquid surface to the CG. And we can calculate that by adding 1 meter and 1 meter. So H bar is equal to 2 meters. And in curved surfaces, H bar is equal to Y bar. And the distance of CP below CG is eccentricity E. So we're ready to solve for FH, which is equal to gamma of water is 9.81 kilonewtons per cubic meters, and our H bar is 2 meters, and the area of the projected rectangle is base times height, wherein our base is 5 meters, our height is 2 meters. FH is equal to 196.2 kilonewtons. If we illustrate that in the figure, this is FH. In letter B, we are asked to solve for the total hydrostatic force F, which is equal to the square root of FH squared plus FV squared. But we need to solve for FV first, which is equal to gamma volume. Solving for volume, we need to trace vertical lines from the endpoints of the curve up until the liquid surface. So from point B, we draw a vertical line up until the imaginary liquid surface. See now, in this case, we have an imaginary liquid surface because the water is below the curved gate. Again, in this case, we have an imaginary liquid surface because the curve, or because the water is below the curve. You notice that in the previous problem, we don't have an imaginary liquid surface because the water is above the curve. Next, we draw a vertical line from point A up until the imaginary liquid surface also, so that the enclosed area is the area we consider for our volume. So we have area 1, this area, and area 2, which is this rectangle. So volume is equal to area 1 plus area 2 times the width of the gate perpendicular to the paper, which is 5 meters. Next, we solve for this horizontal distance from point C by again considering this right triangle. To solve for this distance, we simply have 4 cosine 30 degrees, which is equal to 3.46 meters. And to solve for this horizontal distance, we simply subtract the radius 4 meters and this 3.46 meters, which is equal to 0.54 meters. Next, we solve for area 1, which is equal to the area of the sector minus the area of the triangle. To solve for the area of the sector, we simply have area of the circle pi r squared over its central angle of 360 degrees is equal to the area of the sector over its central angle of 30 degrees. Substituting our radius r, which is 4 meters, we get area of the sector equal to 4 pi thirds square meters. We're now ready to solve for area 1, which is equal to the area of the sector previously computed minus the area of the triangle, which is 1/2 base times height, where our base is 3.46 meters and our height is 2 meters. So area 1 is equal to 0.729 square meters. And for area 2, that is area of the rectangle base times height, where our base is 0.54 meters and our height is 1 meter. So area 2 is equal to 0.54 square meters. We now solve for the volume by substituting the values of area 1 and area 2. And that is equal to 6.345 cubic meters. Now we can solve for FV, which is equal to gamma, which is 9.81, times the volume previously computed. So FV is equal to 62.24 kilonewtons. And finally, we can solve for the total force F by substituting the values of FH and the values, by simply substituting the values of FH and FV. So F is equal to 205.84 kilonewtons. If we illustrate FV and F in the figure, this will be FV and this will be F. And in letter C, we are asked to solve for the location of the vertical force FV from point A. So let's call that distance Z. And let's call the distance of FV from point C as distance X. Z is equal to the radius 4 minus the distance x. Here you do note that for circular curves, F passes through the center of the circle, which is at point C. And if F passes the center at point C, the moment at point C is equal to 0. Because if the force passes through the point where you are taking moment at, the moment is equal to 0. So if we take summation moment C equal to 0, we have the summation of moment of the components FH and FV. For FH, it tends to rotate counterclockwise about point C. So having our notation counterclockwise moment negative and clockwise moment positive, this is a negative moment. So we have negative FH times the perpendicular distance of FH from point C is 1 plus E. So E here can be solved using the formula. And for the moment of FV, it tends to rotate clockwise about point C, so that's why positive FV times the moment arm from point C is x. So x is unknown. So we will solve for x in this equation. FH and FV are solved a while back. So first, we solve for E, which is equal to Ig over A y bar. And the Ig, or the moment of inertia of our projected rectangle, is simply BH cubed over 12. And the area is base times height. Substituting, our base is equal to 5 meters and our height is 2 meters. And the y bar, which is equal to h bar, is equal to 2 meters. Therefore, E is equal to 0.167 meters. Substituting the values of E in this equation and also the values of FH and FV solved a while back, we can solve for X. And X is equal to 3.68 meters. Now we go back to this equation for Z. Z is now equal to 4 minus the value of X, 3.68. Therefore, Z, which is the location of the vertical force, FV from point A is equal to 0.32 meters.